In 1894, Nikola Tesla patented a coil for electromagnets in U.S. Patent 512340, commonly known as the pancake bifilar coil. As he states in the patent, the coil is wound in this manner to maximize the voltage between adjacent wires in order to maximize the capacitance of the coil and thereby cancel out the self-inductance of the coil at its resonant frequency of oscillation. This means that when driving the coil with alternating current at its resonant frequency, the only losses will be those of its natural resistance in the wire, and maximum transfer of energy from the current to the induced magnetic field can be achieved. Note that Tesla's pancake bifilar coil is bifilar only in the radial direction, meaning that adjacent wires spiral outward radially from the center. This led me to wonder, if a coil can be wound in such a manner with high radial capacitance, why couldn't an electromagnet? So I started out on my journey of creating a bifilar electromagnet. I started out using CAD tools to model the electromagnet structure and coil windings in order to figure out how to wire up the coil. Each successive layer of windings needed to be connected in series to the coil 2 layers away. In other words, all the odd layer windings needed to be connected in series, and all the even layer windings needed to be connected in series. Then finally, the last outer odd winding needs to connect to the inner start of the even windings. My goal was to create a coil with 14 windings in total, but the CAD tool I was using started slowing down tremendously after about the 3rd winding, and I did not want to replace the coil windings, where each were represented with a simple helix, with a stand-in cylinder, because the whole point of modeling was to figure out how to wire up the coil. This caused me to start searching for a parametric CAD tool that could handle 14 helical windings in addition to the structure that held them. One after the other started bogging down after adding just a few coils, each to the point of unusability. Not only that, but the resulting STL files used to represent the model for manufacturing became prohibitively large, on the order of gigabytes. I felt there had to be a better way. Throughout my life, I had played around with computer graphics and OpenGL as a hobby, and a friend had pointed out ShaderToy to me at one point. I was amazed at the creativity and beautiful artwork that people had created just using the OpenGL shading language, or GLSL. Another resource I came across was the amazing online tutorial called The Book of Shaders, where the authors, Patricio Gonzalez Vivo and Jen Lowe, likened the use of GLSL fragment shaders as, quote, the equivalent of Gutenberg's press for computer graphics, end quote. The graphics processing unit, or GPU, in modern computers is the key innovation that makes it possible to create such beautiful artwork by writing fragment shaders whose sole responsibility is to determine the color of the single pixel requested of it. This computation is what is called embarrassingly parallel, because each shader assigned to an individual pixel doesn't need any knowledge about any other pixels in order to calculate its color. As a result, if you have enough computational power to assign a processing unit to each pixel, the image can be computed and drawn at astonishingly high speed. Instead of fragment shaders being used to answer the question, what color should be drawn in this 2D space, I started to wonder if they could be used to create 3D objects by answering the question, what material should be added to this point in 3D space? This led me to the invention of infinite resolution materials format shaders, or IRMF for short. After months of work creating the specification, an online editor, and a slicer for backward compatibility with existing 3D printers, I finally had a way to represent my complex model of the bifilar electromagnet and finished the design of the windings. I 3D printed 3 spindles in order to hold the windings for my 3 coils. It then took many days to hand wind and wire each of the 3 coils. Finally, the coils were finished. I had built a carousel of magnets several years prior and decided to design and 3D print a stand to mount the coils around the carousel. After setting this up, I had challenges driving the coils properly to rotate the carousel, so the project sat on hold for many months. Meanwhile, the laborious experience of hand winding the 3 coils made me think that there must be a better way, so I started investigating the possibility of 3D printing the coils themselves, using a metal additive manufacturing process. Unfortunately, all options were prohibitively expensive. While waiting for funds to print my 18 electromagnets in copper, I once again attempted to rotate the carousel with 3 different sensorless, brushless motor controllers. The first 2 failed, but the third worked beautifully. The amazing thing to me is that the carousel can continue to rotate with only 20 milliamps of current at 12.44 volts, which is only a quarter watt of power. Then one day it dawned on me that the electromagnetic coils I wound only maximized the capacitance of the windings in the radial direction and not in the axial. If I were able to wind 2 coils on each layer and have alternating layers shift their rotation by 180 degrees, then every pair of wires in all 3 dimensions would have the maximum voltage difference between the pairs and thereby increase the capacitance and dramatically drop the resonant frequency of the electromagnet. However, attempting to hand wind this electromagnet would be error-prone and tedious, so I decided to model this using IRMF. This new model became what I have called the Axial plus Radial Bifilar Electromagnet. I am now actively researching how I can print 18 of these electromagnets to mount on my magnet carousel. Fortunately, metal additive manufacturing techniques and devices are getting better at a rapid pace, and prices are starting to drop so that it may be possible to print these soon. My next steps would be to build up enough funds in order to proceed with the production of my envisioned axial plus radial bifilar electromagnets in copper. If you are interested in chipping in, even if it's just a few dollars, it would be very helpful and greatly appreciated. A link is provided below. Thank you for watching and have a great day.